In this lesson, we'll talk about rotational dynamics and the moment of inertia. So what we're going to think about is what is the equivalent of Newton's second law in rotation. So what is Newton's second law? Do you remember? Newton's second law says force equals mass times acceleration. On the AP equation sheet, it looks like acceleration equals the sum of the forces over the mass, or net force over the mass is equal to acceleration. So when we talked about linear motion, we said that a force will cause an object to accelerate. When we look at rotational motion, let's say we have an object, a pivot point, and a rod and an object at the end, and the object rotates around. For a rotational motion, we have, instead of a force, now we're going to have a torque, and the torque will cause angular acceleration. So torque is replacing force, and alpha is replacing A. So let's consider a particle that's traveling around in a circle around a pivot point. We said that the tangential acceleration, or the acceleration here, is equal to the force over the mass. Well, we're going to replace this with some variables that we use in rotational motion. So first, we're going to remember that acceleration that's linear is equal to rotational acceleration alpha times r. That gives us alpha r equals force over mass. And then we're going to simplify it a little bit by putting the r on the right-hand side. So alpha equals force over mr. Now we're going to try to put torque in instead of force. So we have to remember that torque is equal to r times f. So for this particular case, theta is equal to 90 degrees. So rf sine theta becomes just rf. So we can rewrite this to say that force is equal to torque over radius. And then we can replace F with torque over R. This becomes alpha equals torque over m, and we have two r's on the bottom now, so it becomes r squared. This is going to lead us to the rotational equivalent of Newton's second law. This is what you have on your equation sheet. It says that alpha equals the sum of torques over I, or net torque over I. Well, we have to talk about what I is so that you can see where this comes from. So let's introduce I, which is the moment of inertia. The moment of inertia is the rotational equivalent of a mass. So if I have a single particle, I is defined as mr squared. And that's just the definition. It's the mass times the radius of rotation squared. If I have more than one particle, I end up with I equals, let's say I have all of these particles. Each mass is going to add a moment of inertia, and all together we'll get a net moment of inertia. So the total inertia of this whole system is the sum of the inertias of each particle. So I is equal to m1 r1 squared plus m2 r2 squared plus m3 r3 squared. We keep adding it up, and it's the sum of mr squared. What this means is that moment of inertia depends on mass. So if I increase the mass of the object, I'm going to have a larger moment of inertia. So the larger an object's mass, the larger moment of inertia, which means the harder it is to get it rotating. You remember inertia from Newton's first law is the tendency of an object to resist motion. So more moment of inertia is tied in with the inertia of the object. Also, from the radius, the farther away the object is from the pivot point, the harder it is to get the object rotating. And I'll show you an example of that. But in the meantime, the units for moment of inertia are kilograms times meters squared, because there's mass times radius squared. So let's look at an example where we change the distance and it makes it harder to rotate. Let's consider we have 3 people on a merry-go-round and we're going to push them, and they're all on the edge. This is going to have a larger moment of inertia because this has a large moment of inertia because their radius is the most it can be. So it's harder to push these people. But if I have these kids all move to the center of the merry-go-round, I have a smaller moment of inertia now. The radius is smaller, and it's easier to get it rotating. So we've defined for a single particle inertia, moment of inertia equals mr squared. So now we're going to look at the equation that we derived a couple of slides ago, which said alpha equals torque over mr squared. Well, this mr squared we can replace with I. So we end up with alpha equals the sum of torque over I. This is our rotational equivalent of Newton's second law. Even though we derive this equation for a single particle, it applies to all objects of uniform density. For any object of uniform density, the angular acceleration equals the net torque on the object over the moment of inertia of that object. So here's Newton's second law, and you'll notice that these are very similar equations. Let's note the similarities. So this table shows linear motion, variables for linear motion, and the equivalent rotational motion variables. Linearly, we have acceleration is a. Rotationally, we have angular acceleration is alpha. Linear force is the rotational equivalent is torque. Linear motion, mass, the rotational equivalent is moment of inertia. This should say moment of inertia. Here's a chart that shows different I values for different types of objects. So if I had a long rectangular object of length L, its moment of inertia is 1/12 the mass of the object times L squared. These are all different moment of inertia equations. And you'll notice you don't need to learn these equations. If you're told that an object has a moment of inertia, it'll either be a point particle, in which case it's mr squared, or you'll be given the equation to figure it out. So talking about inertia and moment of inertia leads to a vocabulary that I want to clarify. Up until now, we've used what we call gravitational mass. We can also measure something called inertial mass. So the mass of an object can be measured in two ways. We can use gravity by putting it on a triple beam balance, or we can use the inertia of the object, or how the object moves, to determine its mass. Gravitational mass, what we've talked to up until now, is it uses a triple beam balance. It measures the mass while the object is at rest, so we can't have the object move to get gravitational mass, and gravity has to be present. But we can also measure inertial mass. An inertial mass uses an inertia balance or a spring-loaded scale. It's just a different type of tool. It's measured while an object is in motion, so you make the object move and you can use that to measure its mass. And the mass is calculated based on the object's inertia. Now note, gravitational mass is equal to inertial mass. They're the same thing because they're only measuring the amount of matter in an object. It's just a different way of measuring it. Gravitational mass is using gravity, and inertial mass is using the motion of the object, or its moment of inertia. All right, let's do a problem. We have 4 very lightweight disks of equal radii, and they have 3 identical heavy marbles glued to them. We're going to rank the moments of inertia of the disks about this axis in the center. So which one has the greatest inertia and which one has the least? So your reminder is that inertia is equal to the sum of mr squared for each object. So to find out which one has the greatest, we're going to have to look at each separately. So for A, our moment of inertia is the sum of all of these masses. So we're going to have mr squared plus mr squared plus mr squared. So our moment of inertia is 3mr squared. For B, we can say it's a moment of inertia is approximately 0 because the radiuses are pretty small. So the inertia of B is going to be the smallest one. For C, this object in the center definitely doesn't contribute to the moment of inertia. Only these two do. So we have mr squared plus mr squared. And that gives us 2mr squared. Finally, for D, our rotation is now at this point down here. So we have no inertia from this object. We have one that's at radius r, so mr squared, plus another mass at 2r. So that's m, and don't forget to square the 2 also. M times 2r, all of that squared. That equals 4mr squared plus 1mr squared, which is 5mr squared. So in order from greatest to least, we have 5 is the greatest. So ID The inertia at point D is greater than the inertia at point A, which is greater than the inertia at point C, which is greater than the inertia at point B.